So our course is EQN 512 advanced earthquake solution. That is design. And when we are talking design, it is understood it is design of civil structure. We are talking about earthquake resistant design of civil structure. There are other types of structures and systems, maybe electrical system. Okay. We can talk about those, but it's not our focus. Okay. So you can see there are two keywords here. One is earthquake resistant, and then there is an adjective, a prefix, advanced. Earthquake resistant design you have done in the last semester. So you know what do we mean by earthquake resistant design. Here the only thing we are going to add is advanced. So let's recapitulate what is earthquake resistant design. You have done a course on that. Now I ask you to put it in simple language, in your language. What is earthquake resistant design? Why should there be a separate course on earthquake resistant design? Is it different than structural design? So what do we mean by earthquake resistant design? Then I will talk about it. And now everybody should be able to tell at least what is earthquake resistant design, because you have done one full semester course on earthquake resistant design. So what is earthquake resistant design? You have done courses like design of RCC structures, design of steel structures. So is earthquake resistant design different than those?
When we do the normal structural design, then we do not focus very much on the seismic part.
So is it only the difference of focus?
These more concerned about lateral forces acting due to earthquake.
But lateral forces are not only due to earthquake. Lateral forces are there due to wind also.
But at particular location, it may be possibility that the earthquake forces is more dominating than other lateral forces.
So in some areas, for example, the coastal regions in southern India, the wind forces are much more than the earthquake forces. Then
It's a methodology of approach, like doing OD as equivalent study method with energy loss in normal structural design. But in the case of earthquake resistant design, we specifically give.
you are missing the most important thing. What is the most important difference?
Occurrence is more frequent.
Occurrence of?
Earthquake, like the forces we have designed it for. If you designing it for earthquake,
No, earthquake is much more rare than all other forces. And gravity force is always active.
so inelastic behavior also becomes very important.
This is the difference. Okay? So the difference of earthquake resistant design and design for all other forces, including wind, is that in case of earthquake, we allow our structures to undergo inelastic deformation. So there are two questions. Why we allow? If we do not allow it in wind and gravity load, why we allow in case of earthquake? Okay. And second is, if we allow it, how we consider it in our design? Will it make any difference in our designs if we allow it to go into an elastic range? So it means that all other loads, commonly applied loads are dead load, live load, wind load, earthquake. not so common load is blast load. Okay. In blast load also, the structure will undergo in inelastic load. So blast also it will undergo, but normally blast load we are not teaching. Okay. Blast load is a very specialized case on very specific buildings. But as the terror activities and the threat to blast is increasing, it is also becoming more popular, and maybe sometime it may also be included in curriculum. Okay. So other than blast load or missile impact load, the structure remains in elastic load. Wind load, dead load, line load. We keep even under hydrostatic load. If I am designing a water tank, then there is a hydrostatic pressure also. Even under that pressure, we keep our structure to remain elastic. Only under earthquake load, we allow our structure to undergo inelastic deformations. Okay. First of all, why? Why we allow only in case of earthquake?
So because earthquake load are for very short duration of time. If we design for only elastic deformation, the building will be very section size will be very large. It will be for early.
So, because it is for small duration, that's why we can allow.
Direction is very
So for that duration, it can be elastic deformation.
It is because earthquake is reversible. It is a reversible load. It is changing its direction. Okay. The first thing we discussed about earthquake ground motion. So if I plot earthquake ground motion with time, and we also compared it with wind. Wind is also fluctuating load. It is changing with time. Wind is also having dynamic effects. Okay. But under wind load, although that is also dynamic, it is also changing with time. We do not allow our structures to undergo in inelastic. Okay. Only in case of earthquake, because it is reversible. And due to that, the structure undergoes hysteresis. This reversible nature of the load causes hysteresis. And this hysteresis causes inelastic energy dissipation. And we can take advantage of inelastic energy dissipation only in case of earthquake, where is hysteresis. Okay, there we can take. In wind, hysteresis does not occur. It's fluctuating, but it is fluctuating about mean wind velocity. It's not reversing its direction. So we can't take advantage of ductility, advantage of inelastic energy dissipation in case of wind, and we have to design our structure to remain elastic. Okay. Now, if we want to take advantage of this inelastic energy dissipation, how do we take that advantage into account? How can we take that advantage? Somehow we have to consider the amount of inelastic energy dissipation which can occur in my structure. Okay. How did we take this into account in the course which you have already done in the last semester? Response reduction factor. So we take this into account through R, that is response reduction factor. Now, how we decide response reduction factor? Response reduction factor we have obtained using two principles, equal energy principle and equal displacement principle. And using those equal displacement principle, we get R is equal to mu, and using equal energy principle, we get R is equal to square root 2 mu minus 1. Okay, so this is in long period range. structure. and this is in short period. How do we know ductility of a structure? You can calculate if you know ductility. How to obtain ductility of a structure? Yes? Yeah, ultimate displacement or not how you will get ultimate displacement. And yield displacement. Sorry? Okay. Okay, so we will, but how you will obtain? Suppose I give you a structure you are designing, suppose this building you are designing, and I ask you to determine ductility. How you are going to obtain that? What will you do? Sorry, we can find out.
The weakest component in the building, like beam for the
How you will know that it is the weakest component?
Generally, the joints are the weakest components.
If you have properly designed your building, joint will not be there. So you have to ensure that the joint should not be weakest. That's what you have learned. So the capacity design. In capacity design, what we do? We ensure that columns are stronger than beams. Joints are stronger than beam and column both. And then every member is stronger in shear than in fraction. If it is RCC. If it is steel component, then we can allow shear yield. Okay. But if it is RCC, we do not allow shear yielding. That's what you have learned. You have learned the tricks and techniques how to ensure that in your first. So how to obtain this ductility ratio mu?
So we will calculate the deformation for yield by taking the all the component for it, like Fy we will take. From that we will calculate the moment capacity for the moment for.
In short, this mu can be obtained by performing non-linear analysis. Okay. In your first semester course, which you have done, did you perform any nonlinear analysis? Did you learn how to perform nonlinear analysis? Have you done any nonlinear analysis? Do you know how to perform nonlinear analysis of any structure, let us say just a beam, cantilever beam? Can you perform nonlinear analysis? No. So far, you have not been taught that. Then how will you obtain response reduction factor? It is given in code. Okay. So in conventional analysis, R is stress stress. In design modes. For example, for us, it is IS 1893, part 1. Okay. This is under revision. I can share with you the revised copy, the draft, which is under wide circulation. So it will no more be in part 1, then in future it will become part 2, part 3. So for different structures, there will be different parts. So for buildings, RCC buildings, it will be part 2. Okay. So at the moment, the latest is 2016. So as per 2016, it is in part 1. Then it is there in ASC 7, American and EC8 0. And there are other codes. There is separate code for New Zealand. Every country has its own national code and they have their own response reduction factors. And these response reduction factors are not matching. Different codes have different response reduction factor for similar type of structures. The type of construction of RCC structures may be very similar in different countries, but the response reduction factors may be different. The Eurocode has up to 4.5. Our code has up to 5 for RCC buildings. It is being increased up to 6. American code has up to 8. If you do proper tactile detailing, you can use response reduction factor up to 8 in ASC section. Okay. So different codes give different values. What may be the reason? It should be related to ductility. So ductility of a building which is designed and constructed in the similar manner should be same, whether it is constructed in India or it is constructed in America or it is constructed in Europe. The ductility should have been same, but the response reduction factors are different.
Ductility is also affected by the external environment, temperature, and stuff like that.
No, temperature is not a factor.
And there might be
Property, I mean, in the range of the temperatures which we are having, atmospheric temperature variation in different parts of the world, the effect on the material properties in that range is negligible. If it is fire, the temperature goes 600 degrees centigrade or more, then we can expect that the material properties will change. But plus 50 to minus 50, material properties are not going to change. Material properties will remain more or less same.
construction practice like the way like
Quality control may be different.
quality control.
Okay. So of course that is one reason. So one reason for that R is different in different countries is construction practices. But more than that is that these response reduction factors have been used historically. Historical evolution. That is the major reason. These have not come from ductility. These are not really, it should have been equal to mu, but these have not been really obtained from ductility. So mu has not been explicitly obtained. So mu has not been actually calculated. Why? Because it required nonlinear analysis. And the tools for nonlinear analysis were not available earlier, and these are still not being commonly used in design of systems. Okay, so this is based on historical values which people have been used, and judgment is used. So judgment of the code committee, okay, these structures have roughly this much, and these structures have performed in such a way in the past earthquakes. Based on that, these values have been evolved, they have been adjusting, increasing, decreasing, like that it has gone. And that's the reason that in different codes, different countries, these are different. Okay. And if you are using different response reduction factors, the ductility demand on your structure which is designed using different codes will be different. And if the ductility demand is different, the performance is going to be different. So what is the expected performance of a structure designed as per code. You have designed a building. Suppose I come to you, you are my designer. I ask you to design my building, and I ask you what will happen to my building which you have designed if an earthquake comes. So if my building is subjected to an earthquake, what is going to happen to my building? What will be your answer? It will be no longer serviceable. Okay.
But the benefit might allow for minimum damage of life.
Minimum damage of life. So you mean to say that some of my family members will die?
In case of earthquake, structure will not collapse.
Sorry?
Structure will not collapse.
Structure will not collapse. What does that mean? When you say structure will not collapse, what does that mean to me? For me, even if a crack occurs, it is collapse. What do you mean that a structure will not collapse? What will happen? You give me the scenario which I can understand.
What is the benefit will be standing? Like if it is a.
You mean all the partitions wall will fall and wave frame will be standing. Standing means what? It will be intact.
It will not be intact, it will have cracks, but it will not completely collapse.
So it means that it will be at the verge of collapse, but it will not collapse. That's what you mean. What implication it has to me? Will my investment be safe? I will put whole of my life saving in constructing that house. Will it be okay? Will I be able to sell my house to somebody? Let's say in 50% cost, will I be able to? So how much will be my economic loss? Will my investment will go fully? 20%, 50%, 80%?
Yes, that value.
Sorry?
Only scrap value.
Scrap value of what? I have to even dump that concrete. Municipality will charge me for dumping. I have to pay for the truck which will take that debris and I have to dump it somewhere. So scrap has no value. So many RCC elements are standing in our lab. If you go there, so many RCC. We are saying, please take it free. Nobody is taking. So there is no scrap value for RCC. You have to pay for dispose of.
The possibility of public domain earthquake is very less. But once it happens, then nothing can be done.
So can you ensure me that that earthquake will not affect my building? So then what will happen to my investment, safety of my family members? I am interested in that. I am not interested in your terminology.
The expected performance can be, the structure will be such that it will allow the family members to escape their house, will give ample amount of time, and then the engines might collapse or there might be some structural damage, but there will be no.
You know how much time you will need if earthquake comes? You have to run from here to outside, open area. How much time you will need? First of all, which side you will run? Suppose earthquake comes here. Which side you are going to run? Oh, you will remain in the building itself. He is talking about that you can run outside there. So if you want to go outside, if you need that much time from earthquake, that you can go outside the building to a safe place. Suppose you are here. This is very important exercise. In Japan, in the schools and in Europe, here we do not do. Even our earthquake engineering people do not know if earthquake comes, which side we will run, where we will go. So there has to be a place which should be safe. Okay, so everybody should reach that place. Otherwise, what may happen? What happened in Bhuj? The people who were on the street, because the buildings fell over that, those children, that was 26 January, those children were having that Prabhat Feri, and the buildings collapsed on them. People on the street died because of earthquake. So here, if you are there, which place? I just want, you are half earthquake engineering experts so far, one semester you have already done. Where will you run? Where will you go? Suppose you are standing in this building. Which side you will go if you are to go? Of course, there is one gate. There is no other gate. You have to get out from that gate. Which side you will go? Will you go towards this side? Or that side? Or where? This side. How you will reach this? You have to go that side and then.
If there is also somewhere to go, then this side will be.
How will you go? Will you break the door?
No.
So then how you are going to? You know the situation of this building, na? Currently you are sitting in this building. So in this building, where will you go?
So towards the lawn in front of seismology. From towards the lawn in front of seismology.
Towards?
Lawn in front of seismological observatory.
That is the nearest open place. So go to the nearest open place. Okay. If earthquake permits you, how much time you will need to reach lawn of in front of seismology lab?
At least 2 minutes.
Huh?
At least 1.5 minutes.
Last more than 1 minute? What is the maximum duration of earthquake? That is the total duration. When will the peak come? 10 seconds. Can you do anything in 10 seconds? So if the earthquake is not the large one, okay, perhaps you can reach the safe place. You should do that. That is also important because sometimes what happens, there is a foreshock. Main shock, the building is not collapsing. You can reach the safe place. And then there is an aftershock and building collapses. This has happened in past earthquakes. So at least you should reach safe place, but don't expect that earthquake, the major one when comes, it is going to give you that much time. If the large earthquake is coming, you won't get that much time that you can reach the safe place. In that case, what to do? Sir, at the corner. Why you are suggesting to go at the corner?
Because we basically design the columns to collapse last. So if you select the column and go near the column, the masonry will collapse first, impulse will collapse first. But generally the frame will collapse later. So if we stand near the frame, there's a possibility that the infill doesn't fall on us and the frame doesn't collapse.
Okay. But finally, if the building is collapsing,
Like we need this
if building is not collapsing, then what you are saying is okay. But if suppose building is going to collapse, the slabs or the columns, you have seen what type of failure generally we see? Pancake type of failure. Columns fail, slab one above the other. Okay? Pancake, chapati, एक के ऊपर एक. Okay? So that type of failure we get. Then,
This is the option other than this.
sorry?
Under the direction.
Under the desk.
No other options are available.
If you go under the desk and this slab falls on the desk,
So direct, it is better to have direct impact. If I didn't want to go under this, then it will be directly forward.
see what will happen to this pipe? This will break and puncture into your body. Okay, so we have slightly deviated from the question, but this is also important. What should you do?
There must be an emergency exit.
Emergency exit.
Like
Okay, emergency exit is important. Okay, there should be sufficient exits so that you can reach the nearest open place. Okay, quickly. Agree. But that is not the end. That is not going to save you. What else we can do? What best we can do? Let us say, if building collapses, the chances are that very rare chances that you will be saved by the rescue room after you have seen people are being saved. But when the building collapses, majority of the people die. So what is the safest place in your room? The safest place is what we call triangle of light. What is triangle of light? When the slab is falling, okay, it will never be perfectly flat. Suppose there is some debris here. The slab will fall like this. And by chance, if you happen to be here, if you are lying here, you may be safe. So this is called triangle of life. This is our triangle of life. Where will be the triangle of life? In this room, can you identify triangle of life?
In between, so there is a column and the limit of the beam. In between, center of the beam and the column.
Between the furniture. So if you lie down between the furniture, there is, I'm not saying you will be safe. Please do not blame me later. I am saying that there are some chances that if this falls, this will crash, but still it will have some more. So chances are there that here some gap remains. Okay, so no other place which is safe. Going under the desk, generally when we do the exercise, I mean in schools that exercise is done, NDMA is also doing those exercises, National Disaster Management Authority. Drills are, mock drills are done. In Japan they do it routine in schools. So they tell the students to go under the desk. Okay, why they tell to go under the desk? Because what is assumed there? It is assumed that the building is not going to collapse. Non-structural component these can form. So if a fan falls, or there is a false ceiling that falls, or there is a TV set which falls, this can save you from those. But this can't save you from the slab. If the slab is collapsing, the beam and slab itself is collapsing, it can't save you from that. So non-structural components, small components, when those are falling, or maybe even if this brick is falling, perhaps it can save if you are inside. But if the slab itself collapses, it can't. Okay. So now let's go back to our question which we were discussing, that what will happen to my building which you have designed? You have designed as per code. What will happen to my building? What will happen?
Few of the family members will not die.
Sorry?
Few of the family members will be alive.
Few will die. That's the correct answer. And in fact, that is also not the correct answer, because even you do not have any mechanism to ensure that. Where have you checked that my building will not collapse? You can say that code tells you that. Code doesn't tell you. If you read the code nowhere tells that your building is not going to collapse. Up to 2002 version, it used to say. So if you read the preamble of the code up to 2002, it was saying that the buildings which are designed as per code are intended that these will not undergo major damage during a minor earthquake, and these will, as far as possible, something like that. So in very loose terms, it was saying improbable, or in sense of some probability that most probably your building will not collapse. Okay. Now that has also been removed, and if you read the current version, 2016 version, it says only one statement, that the buildings designed as per this code are expected to undergo damage. That's it. How much damage? What type of damage? Is my building, as you said, that some of the family members will not die? Code doesn't guarantee even that. Even the whole family will perish if you design this kind. But can you satisfy with that to me as your client? I come to you, please design my building, I will pay you fee. Okay, and then you say whole of your family will die. What is that? So this is what you have learned so far. Clearly, it is not satisfying. Reason for that is that using the code methodology, you can't estimate conventional design method expected performance cannot be estimated. There is no framework to estimate that performance. There are only some do's and don'ts. You do it like this, don't do that, most probably your building will perform okay. But what is this okay? And what is this most probably means? What is the probability? Most probably means what? How much probability I have? 50%, 75%, 95%? That answer is not there in the methodology which you have learned so far and which is being used in our industry. Our industry, whatever you have learned so far, only that is being used. So what I am going to teach you in this semester is still not being used in our industry. But university is just, our industry is just at the verge of crossing that threshold. People are demanding now. So there is demand for this advanced level of earthquake resistant design, where you will be able to tell that what is expected from your building. Okay. If you are designing your structure, you should be able to tell that what is your expected from that design, or depending on my expectation, I want. See, whatever happens, whatever money is required, I am willing to pay. Okay, but none of my family member should be fatally injured during that. Can you do that? Not with the code base, because you do not know what will happen if you design your building as per code method. Whether it will be so good that nothing will happen to the building at all, or it is going to collapse. Only you have good design, do's and don'ts. Okay, so that much is not adequate. That's why we have to go for a better design method, and that better design method is advanced. So what is this advanced here? This is performance based design. Performance based design. You can target the performance. Design for a targeted performance. You can decide. You target the performance. I want this. I do not have enough money. I just want a building. Please design a building for me with minimum cost, so that if earthquake comes, it is very rare, I am not bothered. Okay. But with minimum money I have, please give me a house, cheapest. I have enough money, I won't give me a house, nothing will happen during the day. Okay. So all this can be done through this performance based design. Okay, this is the act. And this you can do only by performing non-linear analysis. Why we have accepted such a method in which we do not even know what will happen to our structure? The reason was that we did not want to do non-linear. We wanted to do linear analysis. Okay. Non-linear analysis is a little more complicated. Tools were not available, software were not available. Now those are available. Okay. So now we can go for non-linear analysis and performance based. So in this course, I am going to teach you non-linear analysis and performance based design. And as I told you, performance based design we will limit to generation 1. Okay. So there are some documents and books which deal with performance based design. I have given a list at the end. Okay.